Mhm.
Okay, so it's my pleasure to present the third and last lecture by Borя Bychkov, and Borya will continue his accounting of I don't know, Hurwitz numbers and related topological recursion questions.
Yes, thank you. So yesterday I did some reformulation of topological recursion and start to generalize the problem from say Hurwitz numbers to this generalized double weighted Hurwitz numbers. And so here you see it adjusted my notes from yesterday. So you see this spectral curve, new spectral curve, which we're discussing now, and these examples of some specializations. And so maybe now let me start with the setup to obtain this this spectral curve. So what is the setup? Let me consider this the following series, that sum of all partitions e to the power psi of h bar j minus I s lambda of p s lambda of s over h bar. So so what I'm doing now, I want to introduce the series which are then produces this spectral curve which was which is written here. So, and we start with this series. It's in fact a kp tau function. It is a kp tau function of it calls usually hypergeometric type of hypergeometric type, or if you would like Orlov-Sherbin kp tau function, due to works of Orlov and Sherbin in around 2000. So what's written here? It's so why it's a kp tau function? It's a, I would say, very well known story, very beautiful and very well known story that I left for you. And what's written here? This s lambda is just Schur functions. S lambda is Schur functions of variables p. So here I mean that we have like p1, p2, etc., and s1, s2, etc. And this Schur function are symmetric in variables x, and this variables x connected to these p variables as a power sums. So this p is p1, p2, etc., and p k is x1 to the power k plus x2 to the power k plus etc. And here this psi is again this psi from the definition from here. Where it's, yes, here. So it's any formal power series. And here we sum up overall contents of the partition lambda. So here, if lambda is some partition of D partition, then we have a Young diagram. So it's like more or less, for me, it's very standard stuff, but maybe for someone not so standard. So and this like I and j, we have a coordinates I and j and I, and so here this j minus I is a content of the boxes of this diagram, and so that it's just a difference between the coordinates. Okay, and this is the capital function, and so it's this z capital is connected to this Hurwitz number stuff, this generalized Hurwitz number in the following way. So let's consider f log of z, then f it's some so the coefficients of this f series in front of the monomial p mu1 etc p mu n is a generalized Hurwitz number. H G mu p mu1 etc p mu n. Yes, and that's why it is so, why it is 10, why it is true. It's like a representation theory of the symmetric group allows us to like present this f series. So if we organize this series for these generalized Hurwitz numbers, then you could rewrite it in the basis of full function, and you obtain this z as I written above. And also a small comment that this, so the operation of it's also I would say standard that the operations of exponentiation and taking logarithm and exponent of the series. If you take a logarithm, you turn to the connected stuff, and if you take an exponent, you turn to the connected, both connected and disconnected stuff. So this, I would say, this f is generating series for connected. I will write Hurwitz numbers, but mean that it's this generalized double Hurwitz numbers, connected Hurwitz numbers, generalized Hurwitz numbers, and z is a generated series.
Short question. And where are your S variables? Your formula
Yeah, I will say
P.
Yeah, I'll say in a minute about it. Yeah.
Okay. I'm sorry to interrupt. So of course it's just the first week theorem, right?
Yeah, you could think about it. Yes.
Yeah. But it's not my question. My question, so as far as I know, so there is, at least to the best of my knowledge, there is no direct combinatorial proof of this relation between topological recursion and short-tau functions, right?
Combinatorial. So
there are some proofs in simpler settings that I know, but basically it's not one step. So we just always go through. through comparison of some cut and join equations or whatever that correspond to it.
I will say not maybe not cut and join equations, but some. So you have to choose a right basis in the so like it's not one step, but it's maybe 3 steps, and you use a representation theory of symmetric groups. So like you could rewrite it in terms of, so you have a Frobenius character formula for Hurwitz numbers, and then you using this character formulas, so you could write this f always log exponent of f in characters, and then characters rewrite in Schur functions and obtain this z. So like, so you have f, then exponent of f, you have a character formula, and then turn to Schur functions.
Okay.
So I would say, I don't know, in fact it's combinatorial because of it uses only that you have a in the example of simple Hurwitz numbers, yes, you have like a cycle of a fixed cyclic type mu and expanded as a product of transpositions, and this gives you some relations. So some you could think about these Hurwitz numbers as a eigenvalue of some operator in the center of symmetry group, the center of group algebra of the symmetry group. So yes, basically it's combinatorial, but you have to use a little bit representation theory. Yes. And so yes, where is this s variables? S variables are hidden here. Yes. So this hg mu that I said that it's generalized Hurwitz numbers, and you should. So here they are hidden like follows. So you should this hg mu, you should expand it in s variables, and then you obtain like the Hurwitz numbers itself, so the number of coverings of such a profile, which rules by p variables and s variables. But here we sum in this h, really we sum up all these guys. So let me maybe write it down. So s variables hidden in hg mu, and you should, so to obtain the real like number of coverings with two fixed profiles p mu1 etc. without p's, yes, mu1 etc. mu n, and say nu1 etc. nu m, you should expand, take a coefficient, so expand hg mu in s variables, and take the coefficient in front of S new 1, etc. New M. And yes, and this, if there will some time today, it's the next generalization. The next generalization of all this stuff is when we are dealing with, so we expand this H in the second tuple of variables, in this S variables, and this H, G, so maybe if time permits today, I will say about it. So we will take into account this as new variables, and obtain some H, M, N of G. So this correlation function, this generating series, these correlation functions with two tuples of variables. First M corresponding to P or S, what would you like, and second N, and it's so it's the next generalization. So it's a very, thank you for the question. Yeah. Okay, now, so what's this is how would the setup for the Hurwitz numbers for this spectral curve, and the plan for today, maybe let me write plan for today, is to describe the main, maybe the main points of how we obtain some closed formulas for this, how to obtain closed formulas for HGM, not these guys, but HGM for generalized Hurwitz numbers, and like on this, the corollaries of this, using this closed formulas, we could prove topological recursion for this. So not for this HGM, but for forms which we construct from this HGM. But nevertheless, using these closed formulas, we prove TR for generalized Hurwitz numbers. And the second one, it's one more generalization. So it's a generalization to these 2-point functions, and also a lot of business there. Okay. So in this, like, okay, nevertheless, it's, I would say, three papers of me, Petya Dudin-Barkovsky, Maxim Kazaryan, and Sergei Shadrin, which is related to all this stuff. Okay, so how we work with this Z and F series, which I define here, we use the Fock space formalism, and what is so for me, I would say that the bosonic Fock space is just a space of in its infinite power series in these p variables. So bosonic Fock space is just a series in these p variables. Let me denote it by f. And so in fact, there is a like Heisenberg algebra of bosons and its representation in this space of series of p variables. And there is a boson fermion correspondence where fermions like a Clifford algebra with and it had representation with the help of this Maya diagram and this creating and annihilating operators psi and psi star. But I'll not. So I don't want to discuss it here, and I just want to do some calculations in this F space, and I have some operators in this F space. So I skip all this stuff about boson fermion correspondence, etc. But in fact, it turns out that it's very useful for us in this problem. So in this F, we have to distinguish elements. It's a one. It's a vacuum vector. Denoted by this, and the linear function. So linear function from F to C, which is which calculates the free term of a series. So the value when all pi's is equal to zeros. Linear function which calculates the free term of the series. So just a value in p is equal to 0. All p's is equal to 0, and it's denoted by this one. And we have operators. Operators J, M corresponding to this psi and psi star. So M d over dpm if m is greater than 0, p minus m if m below 0 and 0 if m 0. And also diagonal operator in the Schur functions basis, deep psi of h, which I denote as in this Schur function basis. So it's it denotes by this identity, so that it has this eigenvalues ij from lambda psi of h j minus I s lambda. It's a diagonal operator. Sorry, diagonal operator in okay, and so it is also well known how to, I don't know the right link, but like, I don't know, 20 more than 20 years known that you can write this Z and F series in terms of this J operators like follows. So we have a Cauchy identity for sure functions. Cauchy identity, which is S lambda of P, so sum over all lambdas S lambda of P times S lambda of S. Yes, sorry for 2S here. It's exponent P I S I over I from 1 to infinity. And then let me rewrite this this Z series, this tau function. So we have e to the power f is z, and it was sum over all lambdas e to this power psi of h j minus psi over all I and j from Young diagram S lambda of P S lambda of S over H bar. And you see here that, so you see here this guy, so not this guy, but this and this. So you could rewrite it, rewrite it like sum over lambda d psi, so to d psi acts on S lambda of P, yes, and times S lambda, this guy remains here, S lambda of S over H. And then use, so it's just this identity is just using the definition of d psi, and here Cauchy identity. You see it here, and we obtain something like this. So, and also we can rewrite. So let me write down, and then you see. So it's e to the power sum s I j minus I over over I h bar act on the on one, so on the vacuum vector. So, and here I also, instead of this PIs, I use this operator j minus I, which means that we multiply by p minus m and write this vacuum vector here. So it's just a rewriting this using the Cauchy identity, rewriting this Z function, Z series, and we obtain this representation. And also the last step to obtain like correlator from our generating series. Now, so what we had like this HGN. It was sum over all mu's HG mu x to the power mu1, etc. x to the power mu n, and the HN is a sum over all. I'm not sure that that this notation was, but nevertheless, 2g minus 2 plus n HGN. And so what's how this HN and Z are connected to each other. So this is the also connected. So connected in the sense of coverings, connected series for connected numbers, and it connects with Z series, Z tau function, like follows. So if we turn to the disconnected ones, this means disconnected. This dot means disconnected. Then it's just so we should change p variables to x variables. So I can write like follows. Just a way to write that it's just the same series, but in different variables written. So in this identity, nothing hidden. Just rewrite in right letters. So I'm saying that instead of these p variables, we write x variables. But you see, it allows us to
no factorial, so it's not Taylor series. No?
Yeah.
No.
But you just take the right coefficients of the z and yeah. And now, in fact, using again, so yeah, you see, we have this z here is equal to this, yes. So instead of and here we take a derivative and then puts all p's are equals to 0. So what does it mean? It means that we apply these j operators with positive indices, and then taking the co-vacuum vector, taking this linear function of this series, and I can rewrite it in the as follows. Is sum then x these variables over mu1 etc mu(n) because of this denominator, because of this m's. And taking the free term, it's this, and then this g mu1 etc g mu(n) deep psi of h bar. So and then what was written here by here, this let me a little bit smaller, try to g mu(n) deep psi over h bar. What exponent si j minus I. Yes. So we obtain the correlator. So here, what's written? What's again written here? We have it's a series in p variables. This is so we work not series, but we work with a series in p letters, and so we take one, then apply some operators to this guy, obtain some series in p variables, and then taking the free term of this guy, we obtain the coefficients in front of this x monom of x variables. And it's just rewriting our generating series in terms of this Fock space formalism. But it turns out that it's very useful again. So because of there is a representation. So why? So for what? For what purpose? Yeah. For what? Purpose. Because of there is a representation of this F in the central extension of Lie algebra GL infinity of matrices with only finite non-zero diagonals. So, and we know how these operators looks like in this representation, and we know how they compute in this representation, and we can again rewrite this correlator function, compute I would say compute all j with minus to the left and all j's with plus indexes to the right indices, and let me note that these j's with plus indexes, they are annihilate vacuum vector because it's just a differentiations, and these j's with minus indexes, they annihilate co-vacuum because of it's just a multiplication by p mu, and then this p mu we put them all to zeros, and it turns out that using this, so there are a long way, in fact, and a long non-trivial technical and not very technical statement, but in the end we obtain some using this computing all this stuff, we obtain some I would say closed formulas. So maybe I can for you to imagine how it looks like, write down maybe at least a part of this closed formulas. So yes, for what purpose we have a nice representation of f in J infinity, which is the space of matrices. And so what? And again we compute, and we know computation relations in this GL infinity, and compute like all j plus to the right, and j minus to the left. That's the very brief description of what we're doing. And so what we obtained finally, and then sorry, yes, and then we use this. So we have a spectral curve, so we have a change of variables instead of this instead of these x variables, we write z variables as so x of z is equal to z to the power z times e to the power minus psi of phi of z. And finally, we obtain some equations in z variable, some functions in z variable, and we're able to prove that these functions in z variables are good enough to satisfy this quadratic loop equation, linear loop equation, and projection property. So how it looks like theorem, again by 4 authors, like 2020, I think. It looks like follows. This AGN is a coefficient in front of each part of this power of the following guy. The gamma UI product overall VK is from gamma omega k plus some unstable, I would say unstable summons. And who is this U? So we have here a summation overall, just simple graphs. Gamma n is a set of simple graphs on n vertices, v1, etc., vn, and the capital set of its vertices and edges, sets of vertices and edges of gamma. So this omega ik, it's a weight on edges, and this u capitals are some operators in z, in this z small variables, and they looks like follows. So maybe it's not very good color. Omega ik is this guy, so it's exponent to the power so you see it's not very so why you could say why I'm writing all this stuff. Maybe I should stop at some moment, but I want to say that I said closed formulas, but you see it's not so close. It's not. It's rather big, and but it turns out that you could work with these formulas. So it's not closed. I mean, there are no explicit equation. We have a sum overall graphs, some simple graphs, and we have this like huge weights, and also this u operator. It's a weight on edges, yes, and it's an operator u, and I should denote this S capital guys and this Q and D guys. It's not very hard, but it takes time. But and U capital is also some operator, which is quite huge. But in that variable, but it turns out that it's possible to work with these equations, And to prove, so maybe I should, I will not write this U, and also this D and Q and this, so S of U, in fact, it's just a e to the power minus U, or e to the power U minus e to the power minus U over U. So G just the differentiation. Z and Q is some, so maybe Q is this guy, so it depends on psi, you see, and Y and Z, so all these guys from the beginning are they live here, but it turns out that we are from these formulas we prove quadratic and linear loop equation. So we prove that there are this huge guys are good enough near the ramification points of the spectral curve. So if to speak the truth, it's strange that what I said a second ago, because of we would not have an explicit equation of spectral curve, because of we have a formal series psi which involved there. But as I said yesterday, there is another formulation of reformulation of quadratic these loop equations, which we're using here. So it's like you can think about it like the space of, instead of thinking of some forms which are odd or even near some points, you could think about space of functions with some properties that they are with some fixed basis, and we can describe this basis and prove that these guys lies in this space. But it's I think I need one more or maybe more lectures to describe it in details, but nevertheless it's possible to prove this quadratic and linear loop equations, and also it's possible to prove so it's possible, so we, maybe I don't know, theorem, not so in the very general family, for the very general family, so for the very general family of psi and y of z, we prove the projection property holds. The projection property holds, so it means that there are no poles except of the poles in the zeros of dx over x, the critical points of x, so that there are no poles, poles except of in the zeros of dx over x. So this again, the loop equations we prove in full generality. It holds for any psi and y of z. And projection properties are not in full generality, but all this, so all known Gurewitz problems are and much more covered by this general by this families. Okay, so it was a very brief description of this generalization. So to make some stop here, it was a very brief description of this generalization of counting generalized double weighted Hurwitz numbers with this spectral curve x of z exponent minus psi of y of z. Okay, I don't know. So I should ask about questions, but I understood that it was really very fast, and I'm not sure that.
I have plenty of questions. Come on.
Yeah. No, so maybe I say one more. So the next point in my plan is the next generalization to this mn point function, but I'm not sure. So I can just state some definitions and results, but maybe it's better to
maybe it's better if we'll just actually stay with this expression, and I'm expecting some comments. So first of all, the first question is simple. So these sums for fixed g and n, are they finite or infinite?
Yeah. So in these z small variables is just a rational functions in z variables. Yeah, and it's the point that so we have like this infinite series in p variables, which we're discussing like these correlators, and in x variables, and after the change of variables x of z, this where it is this.
Second. Yes. So these graphs are actually contain some finite number of elements, vertices and edges, right?
Yeah.
And then, of course, the next question is, so these omegas, they come from this exponent of the quadratic differential operator.
Yeah.
And
but
so it's
sorry.
It's all very close, if not identical, to a Giventhal formalism.
So it's not identical to Giventhal formalism. No, it's a different story.
Different? What differs? What is different? Because in Giventhal we have it's like we in topological recursion how we go from local models to global. So we have some local models which are Kontsevich or BGW tau functions, and then we intertwine them using this quadratic and linear, well, exponents actually of quadratic and linear differential operators. Here,
yes, but here we have, we have always global recursion. So all this this omegas, our n-forms omegas, they are global, and it's global recursion. And
but do we expect that somehow This tau function's hidden somewhere in plain sight here.
You mean?
I mean that's what we might expect if we have just any spectral curve. And so we have local models localized at the branch points. And then indeed, if we get some spectral curve, we get it by intertwining this.
So maybe so what maybe what I don't know, but maybe what I want to comment concerning to your question, that what I didn't say, I think that in the case of simple Hurwitz numbers, we had like simple zeros of this dx over x. And here multiple zeros are allowed, of course, and we have, so in fact we prove this Bouchard-Reinart recursion, not just so generalization of usual recursion where the non-simple zeros of the x are allowed. So here place not only quadratic and linear loop equations, but the higher order equations. So yes, we know how to deal with this stuff. But about, I don't know yet about given tau formalism here.
No, it's I don't know. I was asking Serежа Shadrin about a month ago about that, and well, but I didn't understand his answer. Sorry. Okay. More questions? I don't know, so people don't ask questions no more. But I think, yes, I think that actually it was, this last part was a little well, condensed, but actually instructive. We'll come to it later somewhere.
Yeah. So, and then I have one more part. Yeah, about this.
Maybe. So it's just small announcement that we are about to revive our seminar on online seminar on topological recursion and integrability, and we'll send announcement also to all participants of this online workshop about that.
Yes.
Very short question, maybe suppose we start topological recursion with arbitrary data. So are any properties of the numbers we obtain are guaranteed? You know that if the data are such and such, we're getting Hurwitz numbers or ramified or double Hurwitz numbers, something, these properties we know. But is something guaranteed by the very procedure of the topological recursion? It's not,
So you mean if we have a topological, we don't know anything about numbers, but we have a topological recursion. What the
exactly, start any curve, any x, any I or y or everything.
So then, as we discussed, we have, so theoretically we have our intersection theory. So we know the procedure how to obtain these numbers as some intersection numbers of MGN of some classes, for example.
The classes technically maybe wild.
Yeah. So how to, so like I know maybe two examples of how it works really in the simple Hurwitz numbers and maybe in the case of maps, and yeah, so and there are a few examples that I speak the truth do not understand properly, but that's all. Yeah, it's not easy.
Is there a direct path from Orlov-Sherbina formulas to the spectral curve? So can we show a spectral curve if we have Orlov-Sherbina procedure?
So you see, to obtain this S-sure expansion, we should know something about numbers. So the topological recursion itself, so it doesn't guarantee any of this stuff. For example, if we could these correlators here, yes, where is my pen? These correlators here, and if I generalized a little this correlator, it will not KP tau function, but there are some topological recursion. So I can modify this guide such a way that it will not more a KP tau function.
Still obtainable via topological recursion.
Yes, and some topological recursion will exist. Yeah.
So topological recursion itself doesn't guarantee any KP or any integrable system. There is a article by Inar about that, but not that I understand it.
I'm not sure. Yeah, I'm not sure that definitely it hasn't been KP, but yeah, I'm not sure. Yeah.
Thank you.
Okay, so more questions? Okay, if no more questions, then possibly we'll thanks Bori again for his nice talks.
Yeah, thank you.
And we therefore conclude